You've heard the headline, there's an Earth-like planet right next door orbiting the closest star to the Sun, and it's called Proxima Centauri B. Sounds like the perfect backup Earth, right? In this video, we're going to zoom in on that world, strip away the hype and see what's actually waiting there once you stop reading the headlines and start reading the numbers. Stay with this, because by the end, Proxima B is not going to mean what you think it does. Proxima B orbits the nearest star beyond the Sun at 4.24 light-years away, around 40 trillion kilometers, 25 trillion miles. Its mass is only slightly higher than Earth's, and models say its radius is probably close to Earth's too, so surface gravity should feel similar to what you feel now. Put that together and your brain tags this world as somewhere humans could live one day. That is the first big mistake. The way this planet is usually described is too clean. Similar size, similar gravity, in the habitable zone in the nearest star system. But human habitability is not decided by 2 or 3 numbers. You do not live inside a data table. You live under a star that is constantly hitting your atmosphere, your water, and your DNA with energy and particles. When you hear Earth-like, you're being set up to ignore the most dangerous part of the system, the star. So what does habitable zone actually mean here? In basic astronomy, it is just an energy range. At a certain distance from a given star, a rocky planet could, in principle, hold liquid water on its surface. It does not check if the planet ever had much water. It does not check if an atmosphere is still there, or if that atmosphere has been stable for billions of years. Proxima B orbits at 0.048 astronomical units. 1 astronomical unit is the Earth-Sun distance, about 150 million kilometers. So this planet is only 7.3 million kilometers, 4.5 million miles, from Proxima Centauri, more than 20 times closer to its star than Earth is to the Sun. That sounds like it should cook the planet, but Proxima Centauri is a small, faint red dwarf. Its total brightness is only a tiny fraction of the Sun's. Because the star is so dim, Proxima B can sit close and still only receive about 65 to 70% of the energy per square meter that Earth gets. If you plug that into standard habitable zone formulas, Proxima B lands inside the right amount of starlight. Band. Rocky world. Right energy range. Maybe liquid water. The problem is that those formulas make huge assumptions. They treat the star like a calm lamp, and the planet like a smooth ball with an atmosphere that just sits there. They ignore the high-energy X-ray and extreme UV radiation that is best at ripping atmospheres apart. They ignore powerful stellar winds, flares and super flares, and the fact that red dwarfs can stay active for a long time, especially when their planets are this close in. So yes, Proxima B is in the habitable zone by that simple definition. But that label hardly tells you anything about whether humans could ever stand there and breathe. This is why the phrase "in the habitable zone" is both technically correct and misleading. It is a necessary condition, but nowhere near sufficient. A planet can sit in the habitable zone and still end up frozen solid, boiled dry, or stripped down to bare rock with almost no air. When you see Proxima B is in the habitable zone, you should mentally add, if it still has an atmosphere and water after billions of years of punishment. The real question is not, is it at the right distance, but has it managed to keep its air in its ocean while orbiting this close to this kind of star for this long? Now, look at the planet itself, because that is where most people stop. Proxima B's mass is a bit above Earth's. Depending on the radius, its surface gravity is probably somewhere from slightly lower than Earth's up to maybe around 1.4 G. Your body could adapt to that. You might feel a little heavier, but you're not pinned to the ground. The mass and likely density tell us it is almost certainly a rocky planet, not a gas giant and not a mini Neptune wrapped in thick hydrogen. That means there is most likely a solid surface. If you landed there, you could plant your boots on the ground and walk. So in the narrow sense of can you stand up, Proxima B passes, but walking is not your main problem. For humans, the critical requirements are air, shielding and time. You need an atmosphere at around 1 bar of pressure, with about 21% oxygen and most of the rest nitrogen. and you need that atmosphere to stick around for billions of years. You need an ozone layer or something similar to block most of the dangerous UV and X-ray radiation before it reaches the surface. You need a climate that stays in a temperature range where liquid water can exist on the surface, not just in brief unstable periods. Earth-like mass and similar gravity say almost nothing about any of that. This is the core disconnect. Your instincts grab the familiar numbers: Earth-like size, Earth-like mass, nearby system. You're talking about a rocky world 20 times closer to its star than Earth is to the Sun, under a star that is far more violent than our Sun is today. So the central question about Proxima B is very different from the one in the headlines. It is not, is it in the habitable zone? It is, can a planet this close to a small active red dwarf hold onto a thick atmosphere, liquid water, and a stable climate for billions of years? When scientists model the high-energy radiation Proxima B has probably received over its life, they find that it has taken much more X-ray and extreme UV radiation than Earth, likely around 7 to 16 times as much. Those wavelengths are effective at heating and eroding the upper atmosphere. Other work, including NASA simulations, shows that an Earth-like atmosphere at Proxima B's orbit could be stripped away up to about 10,000 times faster than Earth is losing gas today. If that picture is even roughly right, a world like Earth placed at Proxima B's distance would see its oxygen-rich atmosphere disappear in a tiny slice of geological time, maybe around 10 million years. Earth needed more than 3 billion years to go from simple microbes to complex animals. Those timelines do not line up. You do not get to humans if the atmosphere that makes them possible disappears that fast. So closest Earth mass planet in the habitable zone starts to look less like future home and more like nearest warning sign that the simple labels are not enough. And that pushes you straight into the next, harder question. If the main threat to Proxima B is not its size or its distance, but the star itself, what exactly is Proxima Centauri doing to this planet, flare after flare, year after year, for billions of years? And how lethal does that become for anything trying to live there? So if the real problem isn't the planet, it's the star, the first thing you need to understand is simple. What kind of star is actually sitting next to Proxima B, and how different is it from the Sun you're used to? Proxima Centauri is a red dwarf. That means it has only about 12% of the Sun's mass, and around 14 to 15% of the Sun's radius. It's small, it's cool, and it's dim. Its total light output is less than 1/5 of 1% of the Sun's. In numbers, you're looking at around 0.16 to 0.17 of the Sun's luminosity. So straight away, this is not a normal Sun copy. It is a low-power star that forces any habitable planet to sit extremely close if it wants enough energy to be warm. That's exactly what Proxima B does. It orbits only about 7 to 8 million kilometers from the star, roughly 4.5 to 5 million miles. Earth sits at about 150 million kilometers, about 93 million miles from the Sun. So compared to Earth, Proxima B is more than 20 times closer in. The only reason it isn't instantly cooked is that Proxima is so faint. At that tiny distance, the planet still only receives about 65 to 70% of the energy per square meter that Earth gets. On a basic energy diagram, that looks okay. It lands in the right band for liquid water. But here's the catch. That diagram assumes the star is calm. Proxima Centauri is not calm. So the next question is, how does this star actually behave day to day? And why does that matter so much for anyone standing on the surface of its planet? Unlike our current Sun, which has an 11-year cycle but is mostly steady from hour to hour, Proxima Centauri is what's called a flare star. Its magnetic field is very active. It can twist, snap, and reconnect in violent events that dump huge amounts of energy into the star's outer layers. When that happens, the brightness of the star can jump by factors of 10 to 100 in just minutes to hours, especially in X-ray and ultraviolet wavelengths. Astronomers have watched Proxima Centauri do this. We've seen regular powerful flares, And on top of that, rare super flares that make even the worst solar storms in Earth's history look small. In 2019, instruments recorded a massive flare in far ultraviolet light from Proxima that was one of the strongest ever seen from this star. That's not a rare, once-in-a-million-years event. For a close-in planet like Proxima B, bursts like this are part of the normal environment. If you were on the surface without extreme protection, every major flare would mean a sudden spike in high-energy radiation raining down through the upper atmosphere. So you might now be wondering, okay, but how much worse is this in numbers compared to what Earth deals with from the Sun? This is where the calm, habitable zone label really starts to break. Proxima B is estimated to receive something like 10 to 60 times more X-ray and extreme ultraviolet radiation than Earth does, when you average over long timescales. That's not a small difference. That is an environment where the high-energy part of the spectrum is turned up by at least one order of magnitude, sometimes more. During big flares, it gets even more extreme. NASA modelling suggests that in those events, the extreme ultraviolet radiation hitting Proxima B can jump to hundreds of times the level Earth receives from the Sun. If you look at the X-ray energy flux in some models, it comes out around 163 units of energy per second per square centimetre at the planet's distance. You don't need to love the units. The only thing you need to keep in your head is the ratio. The planet is being blasted with X-ray and UV levels that are way above what Earth's atmosphere has had to cope with. On Earth, our upper atmosphere gets a steady, moderate input of high-energy photons. It heats the upper layers a bit, it drives some chemistry, but our magnetic field and thick air keep the system stable over billions of years. On Proxima B, the upper atmosphere is in a constant high-stress state. Even between flares, the baseline is many times higher than Earth's. When a flare hits, that baseline spikes. The atmosphere gets hit hard repeatedly over millions and billions of years. So why does that instantly wreck the idea of humans living there, even if you assume there is some kind of atmosphere to start with? High-energy photons do a few very specific things to gas sitting above a planet. First, they ionize it. They knock electrons off atoms and the molecules. That changes the chemistry and makes the gas interact more strongly with magnetic fields and stellar winds. Second, they heat it. When the upper atmosphere gets hot enough, the gas starts moving fast enough that some of it can escape the planet's gravity. For hydrogen, which is light, that escape can be rapid. For heavier gases like oxygen and nitrogen, it's slower, but at Proxima B's radiation levels, it is still significant over long times. Over millions to hundreds of millions of years, that process erodes the whole atmosphere. Hydrogen from water is lost first, which means oceans can shrink or vanish. Oxygen can be left behind or also escape depending on the details. Nitrogen, which makes up most of our air, can also be dragged off. For humans, the effect is a three-part failure. The total amount of air drops, so pressure at the surface falls. That makes breathing harder, and if it gets low enough, impossible without a pressure suit. The protective upper layers that block ultraviolet and X-ray light either never form properly or are constantly damaged, which means more radiation reaches the ground. And the radiation dose at the surface climbs to levels that would cause serious DNA damage, cancer and other health problems if you are not heavily shielded. At that point, the picture of "we'll just walk around in light suits under a red sky" collapses. You are no longer talking about a planet where humans can live in anything like a natural way. You're talking about an environment where, if you want long-term survival, you have to bury your habitats underground, pile meters of rock or water over your heads, harden all your electronics against constant radiation hits, and treat the surface like a dangerous work zone. That is not a second Earth. That is a high radiation engineering site attached to a planet that happens to be roughly Earth-sized. And remember, this is only one part of the problem. If the star is this aggressive and the atmosphere is being pushed and stripped this hard, what is happening over time to the actual air and water budget of Proxima B? And how fast can a supposedly Earth-like world be turned into something much closer to a bare, irradiated rock? How long does an Earth-like atmosphere actually survive next to a star like Proxima Centauri, at that tiny distance of a few million kilometers? That is the real test for Proxima B, and the numbers from the models are brutal. When NASA Goddard teams ran simulations of an Earth-style nitrogen-oxygen atmosphere placed where Proxima B orbits, they found that gas does not leak away gently. Under Proxima's high X-ray and extreme UV output, the upper atmosphere heats up and escapes as a strong flow. And the loss rate can be up to 10,000 times higher than what we see on Earth today. 10,000 times is not a detail. At that speed, the oxygen content of an Earth-like atmosphere can be effectively stripped in something like 10 million years. 10 million years sounds large on a human scale, but compared to Earth's 4.5 billion year history, it is nothing. Complex animals on Earth took more than 3 billion years to appear after the planet formed. Human-level intelligence arrived only in the very last fraction of that timeline. So if you place an Earth-like planet next to Proxima Centauri and its atmosphere only survives in a thick, oxygen-rich form for around 10 million years, that is not enough time to naturally run the whole sequence from oceans to microbes to forests to humans. The atmosphere clock runs out long before evolution has a real chance to reach our stage. That is the first key point. By the time you're even thinking about sending people there, the atmosphere that would make it easy for them may already be gone, so you might ask, is this just a short, violent early phase, or has Proxima B been overexposed for its entire life? When scientists add up the high-energy radiation over billions of years, they do not get a friendly answer. Proxima B is estimated to have received roughly 7 to 16 times more XUV radiation than Earth has. XUV means X-rays plus extreme ultraviolet, the energy range that is especially effective at heating and accelerating the upper layers of an atmosphere. It is not the gentle, visible light that warms your skin, it is the part that tears molecules apart and drives gas escape. If Proxima B ever started with Earth-like oceans and an Earth-like atmosphere, those XUV photons have had billions of years to attack them. Hydrogen from water molecules is the easiest to lose, because hydrogen atoms are light and can reach escape velocity more easily when the upper atmosphere is heated. Over time, that means whole ocean equivalents of hydrogen can be lost to space. Most models agree that at minimum, Proxima B could have lost at least the hydrogen corresponding to one Earth ocean. Some studies with more aggressive flare and wind histories say the loss could be much higher, potentially removing most surface water and leaving only deep ice or small pockets of liquid water underground. In other words, even before you worry about air, you have to accept the possibility that a lot of the planet's original water budget is gone. So which is it then? A world that loses only one ocean and keeps some water and air, or a world that has been stripped far more severely? Different research groups have tried to answer that, and they do not land on identical numbers, but they all point in the same direction. Rebus and co-authors in 2016 calculated scenarios where Proxima B might have lost no more than about one Earth ocean's worth of hydrogen by the time the star settled down a bit from its most extreme youth. In their more optimistic cases, that leaves enough water to stay habitable in principle, if an atmosphere also survives. Arapetian and colleagues in 2017 took a different approach. They used more intense assumptions for Proxima's flares and stellar wind, and that they followed how those conditions would strip an atmosphere like Earth's. Their result was much harsher. In their models, a whole Earth-like atmosphere can be lost in about 10 million years. That is the same short timescale you saw in the NASA simulations. So you have one set of work saying at least one ocean gone, maybe more, and another saying the entire atmosphere can disappear on geological fast forward. They disagree on the exact amount of loss, but they agree on the key point for you. Keeping a thick, stable, human-breathable atmosphere on Proxima B is extremely difficult. This is why when you hear Earth mass planet in the habitable zone, you should mentally add, under atmosphere-destroying conditions that most models consider severe. If your goal is humans breathing comfortably on the surface without extreme technology, Proxima B is not playing on normal difficulty. It is playing on nightmare mode, where the default outcome is either losing your air, severely changing its composition, or freezing and drying the planet out. So what does that actually mean for you personally at ground level in your lungs and in your blood if you somehow arrive there? Humans need a few basic conditions. You need roughly 1 bar of pressure at the surface, like we have on Earth at sea level. You need about 21% oxygen, with the rest mostly nitrogen as an inert background gas. You need enough ozone or similar shielding in the upper atmosphere to block most of the dangerous UV, and you need temperatures where liquid water can exist without everything instantly freezing or boiling. On Proxima B, the simplest reading of the physics gives you 2 main end states, and both are bad for unprotected humans. In one extreme, the atmosphere is mostly gone or very thin, like Mars. Mars has less than 1% of Earth's surface pressure. In that kind of environment, without a pressurized suit, the pressure is so low that water in your saliva and the moisture on your eyes starts to boil at body temperature. Your blood does not explode, but it starts to form bubbles. Breathing is impossible because there is almost no air to inhale. You lose consciousness in seconds. This is what happens when atmospheric loss runs almost to completion, and nothing significant is left to support surface life. In the other extreme, the atmosphere survives, but in a very different form from Earth's. One of the modelled uninhabitable states for Proxima B is a cold, dense atmosphere with around 10 bars of pressure at the surface, made mostly of oxygen and carbon dioxide, sitting at a global average temperature of about 257 Kelvin, which is about minus 16 degrees Celsius, or about 3 degrees Fahrenheit. That is a world with air 10 times denser than Earth's, dominated by oxygen in a way that is not biological but chemical, left over after huge amounts of water were broken apart and the hydrogen escaped. For humans, that second state is just as bad, but in a different way. At those pressures and that high in oxygen fraction, the gas is toxic to your lungs and nervous system over time. Fire risk goes way up. Materials that are safe on Earth can burn or degrade quickly. The air is not a gentle oxygen-nitrogen mix. It is a highly oxidizing fluid that eats away at organic materials and infrastructure. The temperature is well below freezing for pure water, so any surface water would need salts or other factors to stay liquid. You're not walking around in a jacket under a red sky. You're inside a cold, dense, chemically aggressive atmosphere that you cannot breathe and that tries to destroy your equipment. Both ends of that spectrum are hostile. Either the air is too thin to keep your blood stable without a pressure suit, or it is dense, cold and chemically dangerous. The popular label habitable is carrying far more weight than the data supports. It only means liquid water could exist somewhere, not a human can walk outside in light gear and live a normal life. And all of this still ignores one more major factor. Even if any atmosphere survives, no matter its composition, Proxima B probably does not spin like Earth. With such a short year and such strong tidal forces, it is likely locked into a pattern of eternal day on one side and eternal night on the other. So the next hard question is this: what does a climate look like when one hemisphere is permanently heated by a violent star, the other is locked in deep cold, and your already stressed atmosphere has to try to move heat between them without collapsing completely? Here's the next big problem with Proxima B that almost no headline explains clearly. The year is only about 11.2 Earth days long. That short year means the planet is extremely close to its star, only about 7 million kilometers away, roughly 4.5 million miles. At that distance, the tidal forces from Proxima Centauri are intense. Over time, those forces grab the planet's rotation and slow it down until it locks into a stable pattern. Most models say Proxima B is either tidally locked, with one side always facing the star, or in a near resonance similar to Mercury's 3 rotations for every 2 orbits. In the locked case, you do not get a normal day-night cycle. One hemisphere sits in constant daylight, the day side, and the opposite hemisphere sits in permanent darkness, the night side. No sunrise, no sunset, no spinning blue marble. One side never really cools, and the other never really warms. So the obvious question is, what does that do to a planet's weather and air? On Earth, rotation spreads sunlight around. Every point on the surface gets heated and then cooled every 24 hours, so the atmosphere is constantly being mixed. On Proxima B, if it is locked, the heating is fixed in place. The substellar point, the spot directly under the star, is always the hottest region. The night side never sees direct light at all. Without rotation, you are asking your atmosphere and your oceans to move heat from a permanent hot zone to a permanent cold zone all the time, with no break. If you take a simple view, with thin air and weak heat transport, the answer looks bad. In that picture, the night side becomes a deep freezer. The temperature drops so low that gases that are normally part of the air, like carbon dioxide and even nitrogen, can condense out and freeze onto the surface. Water vapour does the same thing, forming thick ice. You get permanent ice caps and glaciers on the dark side that never melt. That trapped ice is not just frozen water, it is frozen atmosphere. Every molecule that snows out onto the night side is one less molecule circulating over the day side. Over time, that process can drain the atmosphere from the day side and lock it into the night side cold trap. The result is atmosphere collapse. The planet still has gas, but most of it is sitting on the dark side as solid or liquid instead of circulating as air. Surface pressure on the day side drops, winds weaken because there is less air to move. The climate system stalls. If that happened on Proxima B, the day side would slide toward a thin, Mars-like atmosphere, while the night side hoarded most of the gas as frozen deposits. So you might think the story ends there. Locked planet, frozen night side, collapsed atmosphere, hopeless for life. But when teams actually run full 3D climate simulations for Proxima B, the picture gets more complex. Groups led by Turbet, Boutle, Del Genio, and others have taken general circulation models, the same kind of tools we use to study Earth's climate, and applied them to a Proxima B-type world. They include realistic winds, clouds, radiation, and different possible atmospheres. Here's the twist from those models. If Proxima B started with a substantial atmosphere, something with surface pressure at least similar to Earth's, maybe higher, and if it has enough water, the system does not automatically collapse. The thick air can move a lot of heat from the day side to the night side. Strong winds carry warm air away from the substellar point. Oceans, if they exist, also help move heat around. In those simulations, you can get a stable pattern where the day side has a region with temperatures above freezing, while the night side stays extremely cold but not so cold that the entire atmosphere freezes out. In the aquaplanet scenarios, where the surface is mostly ocean, the models often show a permanent pond or ocean of liquid water entered near the substellar point. The rest of the planet can be very cold, with huge ice sheets spreading into the dark hemisphere, but the central dayside zone stays warm enough for liquid water. You end up with a planet that, in a strict sense, is habitable, because somewhere on the surface water is not frozen. Nightside temperatures in these cases can still drop far below -50 degrees Celsius, below -58 Fahrenheit in many regions, but they don't drag the whole atmosphere down with them. So does that mean Proxima B is secretly fine as long as it has enough air and water? Not really. That best case outcome from the climate models is still very far from an Earth twin. In that scenario, habitability is limited to a relatively small patch around the substellar point, where the star is always overhead. You get a permanent bright region where conditions might be close to the melting point of water, and a huge fraction of the rest of the planet is locked in deep cold. You do not get broad zones of mild climate stretched from equator to poles like we have here. You get a concentrated oasis surrounded by lethal environments. On the night side, many model runs show temperatures far below -50 degrees Celsius, and in some places much colder. That is worse than Antarctica in winter, extended over half the planet, without any sunlight at all. The Terminator region, the line between day and night, can host extreme winds, as hot air from the day side rushes toward the cold dark side and sinks. Cloud patterns may be thick over the substellar point, which can help reflect some light and stabilize temperatures, but they also lock you into a climate that is balanced on a knife edge. That is another important point. The climate in these models is very sensitive. Small changes in greenhouse gas content, in the amount of carbon dioxide, or small shifts in the star's output can flip the system. Increased greenhouse gas is too much and you risk pushing the day side into a runaway greenhouse, where temperatures climb and water starts to evaporate faster than it can condense and rain out. Decrease them or strip too much atmosphere, and the dayside liquid water region can freeze over, turning the whole surface into a global ice shell. There is no wide, comfortable zone. There is a narrow range where things kind of work, and outside that range, the planet becomes either too hot or too cold very quickly. For human civilization, that is a terrible starting point. You do not get a planet where you can spread out and build cities across continents, grow crops in many climates, and have backup regions if one area suffers a disaster. You get one main patch on the dayside where conditions might be workable with heavy technology, and a vast frozen pitch-black hemisphere where you are not going to put farms or cities. The night side is basically off-limits without extreme infrastructure. Add on top of that the radiation environment you already heard about, and the picture gets worse. Any settlement has to sit in that dayside zone to access light and potential surface water, but that is also the hemisphere constantly facing the flaring star. The same star that is already hammering the atmosphere with X-rays and extreme UV for billions of years is now delivering that energy straight onto your only habitable patch without any rotation to share the load. So even in the optimistic case where Proxima B keeps a thick atmosphere and avoids total collapse, you are looking at a fragile oasis surrounded by lethal cold and constant space weather stress. A small area of marginally okay conditions, wrapped in environments that will kill you fast without serious protection. For a species that builds large, distributed, resilient civilizations, relies on global agriculture, and needs redundancy to survive disasters, this is not a second Earth. It is a cramped survival zone on a world that is very easy to push over the edge. And remember, all of this finely balanced climate behavior is happening while the planet is being hit by stellar winds thousands of times stronger than what Earth sees, and a magnetosphere that gets squeezed and battered as it orbits. So the next question is, what happens when you take this already delicate atmosphere and then crush its magnetic shield under space weather that makes our worst solar storms look mild? You've heard what Proxima Centauri's light does to Proxima B, but that's only half the attack. The other half is the star's wind, the constant flow of charged particles that slams into the planet every second. On Earth, we also get hit by a wind from the sun, but our magnetic field deflects most of it. The boundary where that happens, the magnetopause, normally sits around 10 Earth radii away from the planet on the dayside, so tens of thousands of kilometers out in space. That big bubble keeps most of the solar wind from directly hitting our upper atmosphere. Now, put a similar planet next to Proxima Centauri and turn the pressure way up. Three-dimensional simulations of Proxima B's environment using full magnetohydrodynamics show stellar wind dynamic pressures that can be more than 2,000 times what Earth deals with, sometimes even higher. Think about what that means in simple terms. The same kind of magnetic field that protects us here would be crushed down there. The magnetopause that sits far out from Earth would be pushed so close to Proxima B that it almost touches the upper atmosphere. That is not a rare event in those models. That is the normal state of the system. The shield is basically wrapped tight around the planet, with very little room to spare. You might ask, okay, but maybe it just stays like that. Small, tight, but stable. Could life or humans at least count on a constant level of protection, even if it's weaker than Earth's? The answer from the models is no. Stability is not what you get there. Those same simulations show that as Proxima B moves around its 11-day orbit, the stellar wind conditions change a lot. The wind pressure can swing by 1 to 3 orders of magnitude, meaning it can get 10 times stronger, 100 times stronger, even 1,000 times stronger than its baseline value, and it can do that on a timescale of roughly a day. When that pressure rises and falls, the magnetopause moves in and out. In some runs, its distance changes by a factor of 2 to 5, so one day your magnetic bubble might be, say, a few planetary radii out. This next day, under a stronger wind, it gets shoved inward to only a little above the atmosphere. In everyday language, the planetary shield is not a fixed, calm shell. It is pulsing, shrinking, and expanding like a stressed lung, sometimes so compressed that the planet's magnetic field lines connect directly to the star's field. That connection is bad news, because it opens channels along which energetic charged particles can stream straight down into the atmosphere. Instead of sliding around the planet, the wind can dump energy directly into the polar regions, into the upper layers of the air, and into any infrastructure you built there. On Earth, big geomagnetic storms that disturb our magnetosphere and pour particles into the poles are rare and already dangerous. On Proxima B, events like that can be frequent and much more intense, baked into the basic behaviour of the system. So then you might try a mental escape hatch. You might think, fine, what if Proxima B just has a stronger magnetic field than Earth? A more powerful dynamo in its core, generating a bigger shield? Would that fix it? The problem is, the physics of magnetospheres around planets orbiting them dwarfs is not that simple or that forgiving. Studies of similar systems, including the TRAPPIST-1 planets, show that even when you assume a strong planetary field, the magnetopause still gets compressed dramatically by the high-pressure winds close to these stars. For Proxima B specifically, the stellar wind is so strong that even a magnetic field several times stronger than Earth's would still be shoved inward. The standoff distance, the place where the wind and the magnetic pressure balance, sits so close to the planet that parts of the upper atmosphere can actually extend beyond the protective region. That means some of the gas you are desperately trying to keep is literally outside the magnetic shield, where it is fully exposed to direct erosion by the wind. In that situation, a stronger magnetic field doesn't solve the core problem, it just slightly adjusts where the damage happens. On top of that, the varying wind can distort the magnetosphere into shapes where field lines open and close rapidly, again giving particles easy access to the upper atmosphere. There is no configuration where you get a wide, stable, protective bubble like Earth's, sitting calmly out at 10 planetary radii, soaking up the hits. In almost all realistic cases, you end up with a tight, stressed shield that is constantly being squeezed and punched through. So what does all of this mean for you as a human actually trying to live there? Not just draw diagrams of the system. First, surface radiation levels become a serious concern even if some atmosphere survives. At high latitudes where magnetic field lines dip down and connect to space, energetic particles will stream in frequently. On Earth, radiation doses from space at ground level are low and normally safe. On Proxima B, the combination of a thinner or damaged atmosphere plus a stressed magnetosphere means that doses could regularly jump above modern safety limits, especially during active periods. Long-term exposure in that environment without heavy shielding is a recipe for cancer, cataracts, and DNA damage. It is not a background you want for children, for workers, for anyone you expect to live a full lifetime. Second, your electronics take a beating. Every strong disturbance in the magnetic field can induce currents in long conductors, just like geomagnetic storms do here, but stronger. Power grids, long cables, even parts of spacecraft and habitats can see induced voltages and currents that damage components. Satellite systems in low orbit, if you could even keep them there, would face frequent particle hits and charging events. On Earth, we worry about a Carrington event-level solar storm, as a 1 in a century or 1 in a few centuries danger for our power systems. On Proxima B, equivalents or worse could be regular features of the environment. Your infrastructure has to be built from the ground up to handle constant radiation and constant space weather, not just rare storms. That means heavier shielding, more robust electronics, redundant systems, and a lot of mass and complexity. Technically possible, maybe, for a very advanced civilization, but extremely expensive and failure-prone. All of that pushes the scenario for humans from living on a planet to operating a permanent high-risk facility. You're not spreading out across continents under open skies. You're sitting under rock, inside metal, watching radiation meters, and timing your outdoor work around space weather forecasts that can go bad very fast. It is not a place where you casually build farms and cities and let people live near the surface. And this is the key contrast that sets up the next part of the story. Because if you just looked at Proxima B's gravity and average temperature estimates, you might think, okay, it's a little heavier and colder than Earth, but we can manage that. The numbers there look comforting at first glance. But once you mix those almost normal surface conditions with an atmosphere that might be thin, chemically hostile and constantly hammered by radiation and stellar wind, the picture flips. So the next thing you have to ask is simple and very personal. Even if your body can handle the gravity, and even if you could tweak the temperature, what does the surface of Proxima B actually feel like as a place to stand, breathe, and stay alive? Here's the weird part. The one number that actually feels friendly on Proxima B is the gravity, the thing most people worry about first. Based on what we know, the planet's minimum mass is roughly between 1.05 and 1.3 times Earth's, and its radius is probably somewhere between about 0.94 and 1.4 times Earth's radius. Put those together, and the surface gravity likely falls in the range of about 0.9 to 1.4 g. In plain terms, if you weigh 70 kilograms here, you might feel like 63 to maybe 98 kilograms there, somewhere between a bit lighter and carrying a heavy backpack for the rest of your life. That is not fun at the high end, but it is not bone-crushing either. Think about running, because that's a simple way to feel it. If you can sprint at around 32 kilometers per hour on Earth, roughly 20 miles per hour, on Proxima B, you might top out closer to 24 to 29 kilometers per hour, something like 15 to 18 miles per hour depending on the actual gravity. You would get tired faster, your joints would feel more stress, but your muscles and bones can adapt to that range. Human bodies handle 1.4 Gs in short bursts all the time, for example in sharp turns in aircraft. Living there full time at that gravity would be a challenge, but it is not a hard physical limit. So if your only question is, can I stand up and walk around in a normal way, Proxima B basically passes. So where's the problem then? If the gravity is okay, does that mean the surface temperature is also not so bad? Using basic energy balance, you start with the fact that Proxima B gets about 65 to 70% of the energy per square meter that Earth gets from the Sun. Then you assume an albedo, a reflectivity similar to Earth's, meaning the planet reflects a certain fraction of incoming light back to space. Put those into the standard formulas, and you get what's called an equilibrium temperature, somewhere around 234 to 257 Kelvin. That's roughly minus 39 to minus 16 degrees Celsius, or about minus 38 to 3 degrees Fahrenheit. Those numbers sound cold but not insane. Earth's Antarctica gets much colder than that. With the right greenhouse gases and some heat transport, you could raise local temperatures into a range where liquid water can exist at least part of the time. But here is the catch. The equilibrium temperature is an oversimplified average. It assumes the planet is evenly heated and cooled. It ignores the fact that one side may be impermanent day and the other impermanent night. It ignores strong winds, clouds, and the detailed composition of the atmosphere. It's like judging whether a city is comfortable to live in just by its yearly average temperature, without checking if half the year is extreme heat and the other half is extreme cold. On Proxima B, especially if it is tidally locked, the day side could be much warmer than that average and the night side much colder. The presence or absence of greenhouse gases like carbon dioxide and the total surface pressure will shift the real temperatures up or down. If the atmosphere is thin, heat leaks into space quickly and the surface can be brutally cold. If the atmosphere is thick and loaded with greenhouse gases, parts of the day side can get significantly warmer. So the okay-sounding equilibrium temperature hides a big trap. It gives you a false sense of moderation in a system that is probably anything but moderate. Then there is the big unknown that you cannot dodge. Even with good models, what does the surface actually look like? Proxima B's mass and position sit close to the boundary between classic rocky planets and planets that could hold a huge amount of water or volatiles. There are several options on the table. One is that it is a mostly dry rock, something like a heavier, colder version of Earth's continents, with water mostly gone. Another is that it is an ocean world, with a deep global ocean and little or no exposed land. A third is that it is an ice ball, with thick ice covering most of the surface, maybe hiding liquid water deep underneath. Some formation models say the planet could have formed farther from Proxima Centauri, where ice is more common, and then migrated inward, carrying a lot of water and ices with it. Others say it may have formed more or less where it is now, in a region that is not friendly to holding onto volatiles, and then spent billions of years being dried out by radiation and stellar wind. We do not have a direct measurement of its composition, so we cannot say desert rock or ocean planet with confidence. What we can say with much more confidence is that whatever water Proxima B started with has been under constant assault from X-ray and extreme UV radiation, plus those intense stellar winds you heard about earlier, for billions of years. Hydrogen from water is easily lost to space when the upper atmosphere gets heated, and once that hydrogen's gone, you cannot simply rebuild oceans without a new source of water. So even if Proxima B began as a wet world, with multiple Earth oceans of water, it may now be left with only a fraction of that at the surface, locked as ice or trapped underground. The surface you stand on could be bare, dry rock, a cracked, cold desert, or a rough ice shell with very little exposed liquid water. So when you add this all up, what does it mean for you as a human actually trying to live there? Gravity on its own is not the killer. It sits in a range your body can adapt to. Temperature, at least in principle, could be shifted into a comfortable band if you had the ability to alter the atmosphere, add greenhouse gases, or build large-scale heating systems. Those things are not easy, but they are technically imaginable. The real killers are the ones you cannot easily negotiate with: atmosphere retention and radiation. The Earth-like numbers, mass, radius, gravity, average incoming energy, tell a story your brain wants to hear, a story of a slightly heavier, slightly colder cousin of Earth that just needs some engineering tweaks. But when you layer in the real space environment, Proxima B stops looking like a cozy backup home. It looks more like a scarred survivor, a planet that has spent billions of years being blasted, stripped and stressed by its star. If it still has an atmosphere at all, that air has probably been reshaped by loss, processes, chemistry and extreme weather into something that does not match what humans need. And this sets up the next level of tension, because even if you grant Proxima B a substantial atmosphere today, you still have to ask, how do those different possible atmospheres actually behave under a locked rotation, harsh radiation and strong winds? Do they give you a stable, long-term climate with reliable liquid water, or do they sit on a knife edge where tiny changes flip the entire world from marginally okay to totally hostile? So what actually happens when you stop guessing and you let full climate models chew on Proxima B with real physics, real winds, real clouds? Does the planet always freeze over, or can it actually keep liquid water somewhere on the surface? Teams like Turbets, Bootles, Del Genios and others have run 3D global climate simulations for this world under a whole menu of conditions: tidally locked versus a 3-2 spin state, thin atmospheres versus thick ones, Earth-like air versus carbon dioxide heavy air, dry rock versus global ocean. When you give the planet enough atmosphere and enough water to start with, a clear pattern shows up. It is possible to maintain liquid water on the day side. In many of those runs, you get a warm region centered on the point directly facing the star, the substellar point. If the planet is an ocean world, that warm region can extend into a broad eyeball ocean ring, a big patch of open water surrounded by ice that stretches into the night side. The details depend on how thick the atmosphere is and how much greenhouse gas you allow, but the big message is simple: with enough air and water, Proxima B doesn't have to be a frozen rock. It can host surface liquid water under some conditions, especially in that permanent day region. That result is what drove a lot of optimistic headlines. Climate models say Proxima B could be habitable, and technically that's not wrong. The problem is, those same simulations also spit out numbers that tell a much harsher story once you look at the details. Even in successful non-collapsed atmospheres, night-side temperatures can drop far below -50 degrees Celsius, below -58 Fahrenheit in large areas. That is not a minor chill, that is harsh, deep cold, permanent polar night levels of cold stretched over an entire hemisphere. The global average surface temperature in many modelled states sits around 257 Kelvin, about -16 Celsius, roughly 3 Fahrenheit, colder than Earth's mean climate by a lot. Some states are even colder, completely ice-covered, with no open water at all. For dry, rocky Proxima B scenarios without oceans, the models often need very high carbon dioxide pressures to avoid the atmosphere collapsing onto the night side. We're not talking about Earth's tiny carbon dioxide content, which is roughly 4/10,000ths of a bar at the surface. We are talking about up to several bars of pure carbon dioxide, so pressures millions of times higher for that gas than what you breathe right now. That kind of atmosphere is thick, heavy, and extreme. Yes, it can keep the air circulating and the night side from freezing out completely, but it also produces climates that are nothing like Earth's gentle, mixed nitrogen-oxygen blanket. So call these climates what they really are. They are not broad, forgiving Earth with a red sky scenarios. They are razor-balanced environments. Small changes in greenhouse gas content, in surface pressure, in how reflective the planet is, or small changes in the star's brightness, can flip the system between very different states, from icy desert to hot, humid greenhouse. The habitable region, if it exists, is not a wide, robust target. It is a narrow window you have to hit and stay in. Now here is where the tension really ramps up. Most of those climate models do something on purpose. They assume the atmosphere is there and stays there. They do not try to include the long-term erosion from X-ray and extreme UV radiation, or the crushing wind and magnetosphere behaviour you heard about earlier. They are answering a simpler question. Given a specific atmosphere, what does the climate look like? Not, can that atmosphere survive for billions of years under Proxima's abuse? When you take those optimistic climate states and then remember the space weather, the picture changes. That nice eyeball ocean with a thick carbon dioxide atmosphere, or that Earth-like air with liquid water at the substellar point, now has to survive under wind pressures 2,000 times more. Earth's under high-energy radiation fluxes 10 to 60 times higher than what Earth sees, plus frequent large flares. The climate models might find stable patterns over decades or centuries in their runs, but the space weather models say the atmosphere is being eroded hard over millions to hundreds of millions of years. For complex life, and especially for technological civilizations, you do not just need "it works this century", you need stability over billions of years, giga-year timescales, so evolution can run and ecosystems can build resilience. Proxima B's combined picture looks more like this: short windows where an atmosphere is thick enough and temperatures are right enough to allow surface liquid water in that dayside patch, surrounded by long periods where the atmosphere thins, chemistry shifts, and conditions swing to much harsher states. It is not a steady long-term home, it is a world that might drift in and out of marginal habitability. For humans, that distinction is critical. A planet that is barely habitable in the strict scientific sense is, for you, effectively uninhabitable without extreme intervention. Humans are not going to colonize every borderline rock where liquid water could exist in a small region if you throw in multi-bar carbon dioxide atmospheres and insane space weather. To make a comfortable, self-sustaining settlement, you look for places where you can, at most, do moderate terraforming and engineering, not ones where you have to constantly fight the star, rebuild the atmosphere, and shield every square meter of surface. Mars is already pushing the limits of that idea, and Mars is close, relatively calm, and bathed in much milder space weather than Proxima B. Mars has about 38% of Earth's gravity, a thin carbon dioxide atmosphere, and temperatures that swing from cold to very cold. Even that is considered an extreme challenge for long-term large-scale colonization. Now take Proxima B, with similar or higher gravity than Earth, a climate that might only be stable in a narrow dayside patch, a nightside that sinks to deep sub-freezing temperatures, and a radiation and stellar wind environment that constantly attacks your air and infrastructure. Even in the most optimistic Proxima B climate models, you're forced to concentrate any human presence in that permanent dayside zone around the substellar point, where liquid water might exist. You're forced to harden your habitats against radiation, to monitor the star for flares, to prepare for space weather-driven changes in the atmosphere. You're likely dealing with high carbon dioxide levels or other gas mixtures that are not breathable and not trivial to modify. You're not dropping domes and walking outside in light suits. You're building a high-tech survival outpost that has to fight the planet's natural state every day. That kind of world might still be interesting for biology. Microbes, maybe more complex organisms, could find niches in the ocean, under ice or underground, adapted to the cold, the radiation, and the weird light from a red dwarf. But even if those organisms exist, the climate and space weather combination does not give human civilization what it needs, which is room to spread, redundancy, and long-term stability. So when you hear Proxima B could be habitable in some models, translate that correctly, in a narrow range of assumptions, for some period of time parts of Proxima B might hold liquid water at the surface. That is scientifically important, but it is not a green light for colonization. It is a reminder that, even in the best cases, this planet forces humans into a permanent high-risk balancing act, where one bad stretch of stellar activity or one slow loss of atmosphere can push the system over the edge. And if even the good climate scenarios look that fragile, what happens when you focus not on global averages and open water, but on the one thing you cannot negotiate with at all as a human standing on the ground? How much actual water is left, where it is, and whether it's on the surface at all or locked away in ice and rock out of reach. How much water Proxima B actually has is one of the biggest unknowns in this whole story, and it changes everything about what the surface feels like. The awkward truth is, we don't know if it started out as a dry, Mercury-style rock with almost no water, or as an ice-rich planet that formed farther from its star, picked up multiple Earth oceans of water and ice, and then migrated inwards to its current orbit. Formation models allow both options, so the important question is not just how much did it start with. The key question is, how much water can actually survive sitting for billions of years that close to a violent red dwarf, under constant flares and high-energy radiation? That survival problem is what really decides whether you see seas, ice sheets, or bare rock when you step onto that world. If you look at one of the early detailed studies Rybas and colleagues in December 2016, they ran scenarios where Proxima B starts with a good amount of water and gets blasted during the star's most active youth. In their more optimistic cases, the planet loses at most about one Earth ocean's worth of hydrogen before Proxima Centauri calms down a bit. One Earth ocean sounds like a lot, but if you started with multiple oceans, losing one still leaves you with plenty of water, at least on paper. In that picture, the planet could stay wet enough to remain habitable in a narrow sense, if the atmosphere also survives in some form. But later work takes a harder line. Studies that fold in more aggressive flare histories and stronger stellar winds, including Erapetian's oxygen loss work, argue that you cannot just look at a smooth average over time. You have to count the spikes, the superflares, the extreme events. Those flares dump huge amounts of X-ray and extreme UV radiation into the upper atmosphere in short bursts. They drive stronger escape flows, and they repeat over and over across hundreds of millions of years. When you add that up, the total water loss can be much larger than just one ocean. In those more severe models, Proxima B can end up almost dried out at the surface, with most of its original water either gone to space or locked in deep, cold reservoirs that are not easy to reach. So straight away, even before climate details, you're stuck between two pictures, neither of which is great for humans. In the mild loss case, Proxima B might still have a lot of water left, but it's been heavily processed by radiation and long-term escape. In the severe loss case, the surface is mostly dry, maybe with some residual ice at the poles or in shadowed regions, and whatever liquid water still exists is not sitting in broad, open oceans. It's tucked away in much harsher environments. There's another layer to this that makes the planet even more alien from a human point of view. Even if the surface water is mostly gone, you can still get liquid water underneath ice supported by geothermal heat from this planet's interior. This is exactly what we think is happening on moons like Europa around Jupiter and Enceladus around Saturn. They have thick ice shells, but heat from tidal flexing and radioactive decay in their interiors keeps a hidden ocean liquid below the ice. Models for Proxima B show something similar as possible. Take a planet with a cold surface, say around 257 Kelvin, about minus 16 degrees Celsius or 3 degrees Fahrenheit, and cover it with ice a couple of kilometers thick. If the planet has a reasonable amount of internal heat, that heat can slowly melt ice at the base of the sheet. The pressure from all that overlying ice lowers the melting point slightly, and you can maintain a layer of liquid water at the bottom even while the surface stays frozen solid. That liquid layer can be stable for billions of years, shielded from radiation by kilometers of ice. From an astrobiology point of view, that's actually exciting. Subsurface oceans like that could host microbial life, maybe even more complex ecosystems feeding off chemical gradients rather than sunlight. But for humans, this is almost useless as a place to live in any normal sense. You need air, you need light, you need accessible land or shallow seas where you can build and farm. Living in a subsurface ocean under kilometers of ice means you're operating in an environment more extreme than any submarine, with no natural atmosphere and no sunlight, locked away from the surface by thick ice that you have to drill through and maintain. It's a fascinating science target, but it's not somewhere you build cities. So what about the optimistic story that a lot of people liked? The idea that Proxima B is an ocean world, a planet covered in deep global sea, with at least some liquid water on the surface. Even that scenario is much harsher than it sounds once you factor in everything else. First, think about the tidal locking and the day-night contrast. One side of the planet is in permanent light, the other in permanent dark. That creates huge temperature differences between the day side and the night side. Over an endless ocean, that difference can drive very strong winds, powerful currents, and major storms as the system constantly tries to move heat from the hot side to the cold side. Second, if there's very little exposed land, you have a practical problem. Human civilization as we know it depends on land for agriculture, for building heavy infrastructure, for mining metals and other raw materials. You can do some of that from the seafloor, sure, but that pushes you into deep ocean engineering everywhere all the time, with far higher costs and risks. A planet that is almost all water gives you less room to expand in the ways that have actually worked for humans on Earth. Third, you have no idea what the chemistry of those oceans would actually be after billions of years under intense X-ray and extreme UV radiation, with a different atmosphere and different rock-water interactions. They could be very salty, loaded with dissolved metals, or rich in oxidizing chemicals that are not friendly to the kind of life support and infrastructure you want. You might find that large parts of the ocean are chemically aggressive, corroding materials faster than Earth's seas do. That adds another layer of difficulty to building long-lived habitats, platforms, and equipment. Put all of this together, and the ocean world version of Proxima B looks like this in human terms: a deep, cold ocean, maybe in the range of minus 10 to plus 10 degrees Celsius, about 14 to 50 degrees Fahrenheit, under a dim red star that never moves in the sky on the day side, with brutal radiation overhead and a night side locked in darkness and cold. Yes, it has liquid water. Yes, that is scientifically interesting. But from your perspective, it is not a beach planet. It is a hostile, low-light ocean with nasty space weather, questionable chemistry, and little to no land. You could, in theory, see those oceans with microbes designed to live there. You could, in theory, float habitats on the surface, shield them, and try to run a civilization that way. But every part of that plan is several steps beyond anything we have ever done, and you are doing it in a system that is constantly trying to strip your atmosphere, blast your electronics, and bathe your habitats in radiation. Building a multi-billion person civilization in that setting is not just a harder version of colonizing Earth-like worlds. It's a completely different game, where every advantage is gone and every weakness is amplified. And there is one more trap here, a big one, that connects water, radiation, and chemistry in a way that directly attacks one of the main shortcuts we use when we search for life. Around stars like Proxima Centauri, the very same processes that can destroy oceans can leave behind a lot of oxygen in the atmosphere, even if there is no life at all. So the next uncomfortable question is this: if future telescopes look at Proxima B and see oxygen, does that mean living ocean world? Or does it mean dead planet that lost its water and kept the leftovers? On Earth, when you hear, "There's a lot of oxygen in the atmosphere," your brain immediately thinks life, forests, photosynthesis. Here, that shortcut works, because our oxygen is produced and maintained by biology. On Proxima B, that logic can completely flip. Under Proxima Centauri's harsh X-ray and extreme UV output, water molecules in the upper atmosphere get hit hard. They split into hydrogen and oxygen. Hydrogen atoms are very light. They reach escape velocity easily when the upper atmosphere is heated, and thus they leak off into space. Oxygen atoms are heavier, they move more slowly, and a lot of them stay behind. Over millions to hundreds of millions of years, that process can strip away huge amounts of water and leave you with a thick residue of oxygen. Climate and the escape models for Proxima B find fully uninhabitable scenarios where the atmosphere ends up with around 10 bars of oxygen, 10 times Earth's total surface pressure, with zero life involved. So oxygen by itself does not mean living planet in this system. It might mean planet that lost its oceans. If future telescopes look at Proxima B and see a strong oxygen signature, you cannot just copy-paste the Earth rule and yell biosignature. You need to ask, did this oxygen come from living cells, or did it come from billions of years of water loss under extreme radiation, with hydrogen gone and oxygen left behind as waste? The problem gets deeper when you think about the whole spectrum of light coming from Proxima Centauri, not just the total energy. Red dwarfs like Proxima emit most of their power in infrared, with less visible light and a different pattern of ultraviolet compared with the Sun. That difference matters for photochemistry, the way light breaks and builds molecules in the atmosphere. Trace gases like methane, nitrous oxide, and ozone, which we often use as potential biosignatures, behave differently under a red dwarf spectrum. Around a star like the Sun, ultraviolet light efficiently breaks down certain gases so their lifetimes in the atmosphere are short unless something, often life, is constantly producing them. Around Proxima Centauri, the balance shifts, because the star's spectrum does not destroy them as quickly in the same way. That means you can, in principle, end up with atmospheres that have high concentrations of greenhouse gases, or interesting mixes of oxygen and other compounds, without any biology at all. Long-lived methane, nitrous oxide, and other gases can accumulate from purely geological or photochemical sources. For you, that means something very specific and a bit unsettling. You could have a world that, when you look at it from light years away, shows oxygen, maybe some ozone, maybe some methane, the kind of mixture that, around a sun-like star, would scream life. But around Proxima, under its spectrum and flare history, that same mixture might be a non-biological chemical system, driven by radiation, stellar, wind, and surface reactions, not by ecosystems. You could literally step onto a planet that looks alive from a telescope's point of view, yet find no forests, no oceans, just a cold, dry surface, with a high oxygen, high oxygen atmosphere produced by the star itself ruining the water. Now zoom into ground level and think about what that high oxygen, cold, dry atmosphere would actually feel like. Take one of the model scenarios we talked about earlier, around 10 bars of oxygen-dominated air at a global average temperature of roughly 257 Kelvin, minus 16 degrees Celsius, about 3 degrees Fahrenheit. First problem, pressure. 10 bars is 10 times Earth's surface pressure. Even if only a fraction of that is oxygen, the partial pressure of oxygen alone is way past what human lungs and blood can handle over long periods. Above about 1.5 bar of oxygen, toxicity becomes a serious issue, damaging lungs, eyes, and the nervous system. Second problem, temperature. A global average around minus 16 Celsius means many regions much colder than that. You do not have comfortable, mild climates. You have harsh cold almost everywhere, with only limited zones rising near freezing. Without heavy insulation, you are not walking outside casually, you're in full cold weather gear plus pressure protection. Third problem, chemistry. A high oxygen, dry atmosphere is extremely oxidizing. Metals corrode faster. Organic materials, including plastics and many building materials, degrade more quickly, fire risk skyrockets, spark something in that air and flames can spread in ways we are not used to on Earth. So oxygen planet in this context does not mean blue sky and green plants. It means the air behaves like a strong oxidizing agent. It is closer to living in a giant cold chemical reactor than in a natural park. You would have to design every piece of infrastructure, wires, seals, hulls, suits, to survive constant oxidative stress. Even microbes from Earth might struggle in that environment if they are not adapted to intense oxidation. This is not an atmosphere you treat as a free resource. It is one more hostile parameter you are constantly fighting. This is why Proxima B breaks the simple rule that has guided a lot of exoplanet talk so far, the shortcut that says if you see oxygen, you've probably found life. That rule works reasonably well for Earth around a sun-like star, because without biology, oxygen would not stay at our current levels for long. But for planets around mid-dwarfs like Proxima, you cannot use that shortcut. You have to model the star's exact spectrum, the history of its X-ray and UV output, the cumulative water loss, the interaction between radiation and atmospheric chemistry. Only then can you say whether a given oxygen level is likely biological, or just a byproduct of oceans being split and bled into space. For exoplanet science, that is a big change. It means the old picture of find the habitable zone, find oxygen, declare victory is not good enough. You have to treat each star-planet pair as a specific system, with its own radiation environment and chemical pathways. For you as a potential colonist, though, the conclusion is much simpler and much harsher. Even if our next-generation telescopes look at Proxima B and clearly detect oxygen, maybe even ozone, you should not automatically celebrate. You should assume by default that this could be the mark of extreme water loss and harsh photochemistry, not forests and breathable air. In other words, that oxygen might be a tombstone, not a welcome sign. It could be the final chemical trace of an ocean that boiled off or was slowly stripped away, leaving behind a dense, cold, oxidizing atmosphere that is dangerous for humans to breathe, tough on technology, and completely indifferent to your needs. And that leads straight to the next hard reality you have to face, because even if the chemistry somehow lined up in your favor, even if you found a way to deal with the air, you still have to survive the constant radiation being fired at the surface by flares and particles, day after day, year after year. On Earth, when people talk about a big solar storm, they mean something like the Carrington event in 1859, a once-in-a-century or once-in-a-few centuries problem. Our star throws tantrums, but they are rare enough that we treat them as historical curiosities and future risks, not daily weather. On Proxima B, that entire mindset collapses. For this planet, flare-driven space weather is not a rare disaster. It is part of the normal environment. One study of Proxima Centauri's activity suggests that superflares, the really energetic ones, can hit every few hours during active phases. Not every few decades, every few hours. Each one delivers a burst of X-rays and energetic particles across the system. For a planet sitting only a few million kilometers away, that means your worst-case space weather day here on Earth is basically just a regular morning there. So what does that actually do to living tissue if you are on the surface? High-energy protons, electrons, and heavier ions get accelerated during these flares and associated events. They travel down magnetic field lines and slam into the upper atmosphere. If the atmosphere is thin, eroded, or patchy because of all the other processes we talked about, a lot of those particles will make it much deeper, some all the way to ground level. Even with a thicker atmosphere, repeated strong particle showers can push the dose up. For humans without serious shielding, this is not just extra sunburn, it's real radiation exposure. Radiation dose is measured in sieverts, which combine how much energy is deposited with how damaging that type of radiation is to biology. A few millisieverts spread over a year, like what you get from background radiation and a couple of medical scans, is fine. Several sieverts delivered over a short time is not. At doses of around 1 to 2 sieverts, your lifetime cancer risk rises sharply. At around 4 to 5 sieverts, there is roughly a 50% chance of killing an unprotected adult within weeks without medical treatment. In a Proxima B surface scenario with frequent strong flares, unshielded humans could accumulate doses in that range over relatively short periods, especially at high latitudes where magnetic fields funnel particles down. That means standing outside during the wrong flare without heavy shielding is not just risky, it is potentially lethal. Even normal days might push your annual dose far beyond what we consider safe for nuclear workers here on Earth. It is an environment where any serious colonization plan has to track space weather constantly, plan activities around it, and accept that the planet itself is trying to irradiate you whenever the star feels like it. And that's only the direct particle hit. You also have to worry about what these flares do to whatever ozone or ozone-like UV shield the planet manages to maintain. On Earth, big solar flares and associated proton events can damage the ozone layer by triggering chemical reactions in the upper atmosphere. Even then, the global ozone loss is usually a few percent, and the system recovers over time. On Proxima B, you combine a much higher baseline of X-ray and extreme UV radiation with far more frequent and energetic flares. Each major event can generate nitrogen, oxides, and other reactive species that destroy ozone, or its equivalent if the atmosphere has a different composition. If the planet does have an ozone layer or something similar, repeated blows like this can punch large holes in it or thin it out significantly. Those gaps then let intense UVB and UVC light reach the surface. UVB is what gives you sunburn and skin cancer risk on Earth. UVC is even more energetic and is normally almost entirely blocked by our atmosphere. On Proxima B, after a strong flare, UV levels at the surface could jump to values that cause tissue damage in minutes, not hours. Eyes, skin, and any exposed DNA would take a beating. You would not be planning days at the beach, and you would be planning very short, heavily shielded excursions with strict exposure limits. Now combine these three things together, the frequent flares, the high particle fluxes, and the damaged UV shield, and ask a simple question. How do humans actually live on a surface like that without dying young or getting constantly sick? The honest answer is, you mostly don't live on the surface at all, not in the way you picture for an Earth-like world. If you want long-term safer habitation, you're almost certainly forced underground or inside very heavily shielded structures. In practice, that means using meters of rock or packed soil, the local regolith, as a radiation shield. On the Moon and Mars, people already talk about putting bases in lava tubes or under several meters of material to cut radiation down to safe levels. On Proxima B, that need is even stronger. You would dig deep or build habitats that are mostly buried, with only small hardened access points to the surface. Windows would be minimal or heavily filtered. You would rely on artificial lighting inside because the natural light outside is tied directly to flares you cannot control. Your electronics and life support would need similar protection. Circuit boards, power systems, and data lines would all be at risk from particle hits and induced currents during magnetic storms, so you would design them like we design hardware for space probes and nuclear plants, with radiation-hardened components, redundancy, and shields. Everything gets heavier, bulkier, and more expensive. Maintenance moves from go outside and fix it to send a robot or a heavily shielded crew in full gear on a tight schedule between flares if possible. The surface itself in this picture is not a normal environment you live in. It is a high radiation work site. You go up only when you need to, with protective suits and strict time limits, like workers entering a hot zone in a nuclear facility. You do not raise children on the surface. You do not have open-air parks, farms, or cities. All of that stays under meters of rock or water, inside engineered bubbles that you have to constantly monitor and repair. At that point, calling Proxima B another Earth stops making sense. It is not a place where humans can move and adapt the way we did on our own planet. It is not a wide, flexible environment where you can make mistakes and recover. It is a hostile system where the star, the radiation, and the damaged atmosphere force you into underground bunkers by default. The entire planet becomes something closer to a giant, permanent radiation facility where the outdoors is flagged as hazardous area 24/7. And that leads to a deeper question that goes beyond physics and climate. Because even if you can build all this shielding and equipment, you still have to ask whether Proxima B's history and environment give life enough time and stability to get as complex as you are. The star will live for trillions of years, but its early violence and long-term behaviour might have cut off the kind of slow, stable evolution that produced humans on Earth. So the next thing you have to face is this. Even if some kind of life can adapt to Proxima B, does the timeline and the environment ever really line up for human-style civilization? Or are we fundamentally out of place there from the very beginning? How do the timelines of the star and the timelines of life actually line up? And does Proxima B ever get the kind of long, quiet stretch that humans need to show up? Proxima Centauri itself is not short-lived. As a red dwarf, it burns its fuel very slowly. Stellar models say it can shine for trillions of years, far longer than the Sun's roughly 10 billion year main sequence life. So at first glance you might think, plenty of time for life, plenty of time for evolution, no rush. But the part that matters for habitability is not the total lifetime. It's the early and middle phases where the star is most violent and the atmosphere is most vulnerable. For the first few 100 million years to maybe 1 billion years, M-dwarfs like Proxima Centauri are extremely active. Their flare rates are high, their X-ray and extreme UV output is intense, and their stellar winds can be stronger than they are later on. Proxima B is sitting only a few million kilometers away, roughly 4 to 5 million miles. While all of that is happening, that is exactly the window when a young planet is building its crust, cooling its magma oceans and trying to hold on to its first atmosphere and its first oceans. On Earth, that same era was when our planet went from molten to having stable seas and a solid crust, a few 100 million years after formation. So line those up. Earth got its oceans and a long-term atmosphere during a period when the Sun, though more active than today, was still relatively mild compared to Proxima Centauri's early life. Proxima B, in contrast, likely took its worst beating when it was trying to do the same thing. High-energy radiation and strong winds would have hammered its first atmosphere and boiled off or stripped away a lot of its initial water. If the planet ever had a peaceful Earth-style settling-in period, it was much shorter and much more brutal. Then think about how long it actually took to get from first life to humans here. Life on Earth appears in the record very early, probably within the first 700 million years, but humans only appear after about 4 billion years of evolution. For most of that time, life was simple, single-celled, then slowly moved to multicellular, then to complex animals, then eventually to intelligent primates. Even if you are generous and assume everything goes faster on some other world, you are not compressing that into 10 million years. That 10 million year number matters, because that is roughly how long some models say an Earth-like atmosphere could survive under Proxima's harshest early conditions before being stripped down. If Proxima B's first thick, oxygen-capable atmosphere only lasted on that order of time, there is simply no way for slow, stepwise evolution to build humans before the environment changes drastically. The only way around that is if the planet either keeps a dense atmosphere and ocean much longer than the worst-case models suggest, or if it loses them early and then somehow regains a thick, stable atmosphere and significant water later after the star calms down. Some scenarios do try to rescue that. Maybe volcanic outgassing rebuilds an atmosphere after the most violent phase, or water is delivered later by comets or icy bodies from farther out. Maybe Proxima's activity declines enough that, after a rough first half-billion years, the planet settles into a more manageable state. Those are all possible in principle, but none of them are guaranteed, and each adds another layer of if on top of an already difficult picture. So you end up with a split story. On one side, there is Proxima Centauri's huge future lifetime, all those trillions of years where a planet could, in theory, host life. On the other side, there is the early destructive phase where atmospheres and oceans can be heavily damaged or lost, just when they're needed the most. Those two facts pull in opposite directions. Time is available in the long run, but the crucial conditions in the first billion years might have been so hostile that Earth-style, surface-dwelling, air-breathing life never got a fair start. Now that does not mean no life at all. Red dwarf planets could still host biology. It just might look nothing like us and live in places we don't normally think of as habitable surface. If Proxima B kept deep oceans, or if it has a subsurface ocean under ice, microbes could arise and evolve entirely in those protected environments. Deep ocean microbes that feed on chemical energy from hydrothermal vents do not care about flares and UV in the same way surface life does. Subsurface chemotrophs that live in rock pores kilometers down can ignore almost everything happening in the sky. You could even get exotic phototrophs, organisms that use the dim red light that penetrates water under a red dwarf spectrum. They might time their activity around flare cycles using bursts of higher energy light when they come, and hiding or going dormant when conditions get too harsh. Over hundreds of millions or billions of years, those biospheres could become robust and diverse in their own way. But their normal is high radiation, low visitable light, and potentially very little direct access to the open surface. Humans, in contrast, are tuned to a completely different set of boundary conditions. You evolved under a 24-hour day-night cycle, with moderate UV levels, under a thick nitrogen-oxygen atmosphere at about 1 bar, with a stable hydrological cycle, regular seasons, and wide regions of mild climate. Your eyes, your sleep cycles, your skin, your lungs, your entire physiology assume that kind of environment. You're not built to live deep under ice without sunlight, or in a high-oxygen chemical reactor, or under a sky that throws intense flares at you every few hours. You can override some of that with technology, but you're fighting against your own biology the entire time. So even if Proxima B does have life, that life is likely adapted from the ground up to conditions you find extreme. Intense radiation at the surface, dim red light, possibly tidally locked day-night patterns, and limited safe habitats. You're not going to just move into that ecosystem. You would be intrusive, vulnerable, and completely dependent on artificial habitats. You cannot simply take off your helmet, breathe the air, and join the local biosphere, because that biosphere, if it exists, is operating under rules you were never meant to handle. Then there's the bigger step from life to civilization. Complex civilizations need more than life can exist somewhere. They need a few very specific things. First, they need a climate that is reasonably stable over thousands to millions of years. Agriculture, cities, and technological infrastructure all assume that your climate will not randomly flip from ice age to greenhouse on human timescales. Second, they need a radiation environment that is predictable enough that long-lived organisms, like trees and humans, are not constantly being reset by high mutation rates and lethal doses. Third, they need a large habitable surface area, enough land or shallow seas to support large populations, large farms, and large networks of infrastructure spread over many regions. Proxima B, at its absolute best, does not seem to offer that. The climate models say, maybe a stable patch of liquid water on the day side under certain atmospheric conditions, not wide bands of habitable land from equator to pole. The space weather models say winds and radiation 10 to 2,000 times harsher than Earth, not mild background you can mostly ignore. The tidal locking gives you permanent day on one side and permanent night on the other, with all the extremes and instabilities that go with that. Any nice region is limited, and may sit on a knife edge, where small shifts in greenhouse gases or star activity flip it to frozen or overheated. That is a huge problem for civilization. If your only habitable zone is a relatively small area around the substellar point, you do not have the redundancy Earth gives you. On Earth, if one region is hit by drought, another can still produce food. If one coast gets wrecked by storms, people can move inland or to other continents. On Proxima B, if anything disrupts that limited dayside patch, climate shift, flare-induced atmospheric changes, long-term erosion, you don't have a second, third, or fourth region to fall back on. Your entire civilization is concentrated in one fragile zone, under a star that is constantly testing your defenses. So yes, you might get surviving life on Proxima B, you might get microbes in the oceans or in ice or underground hanging on for billions of years under conditions that are extreme by our standards but normal for them. What you almost certainly do not get is a naturally thriving human-style civilization that grows up there on its own. And even if humans arrive from elsewhere, they're trying to install a civilization pattern that evolved under calm, wide, forgiving Earth conditions onto a cramped, unstable, high-radiation patch. And all of that is before you even talk about how hard it is to get there in the first place. Because even if you handwave the atmosphere, the radiation, the climate, and the biosphere, there is still one more barrier that does not care how advanced you are. Proxima B is not right next door in any practical travel sense. It is still more than 4 light years away, around 40 trillion kilometers, roughly 25 trillion miles, which means that just reaching it with real hardware, with people and habitats and shielding, is its own enormous problem. When people say Proxima Centauri B is right next door, they're talking in an astronomer language, not human language. The raw numbers are brutal. At about 4.24 light years away, Proxima B sits roughly 40 trillion kilometers from Earth, around 25 trillion miles. If you fire a spacecraft at 60,000 kilometers per hour, about 37,000 miles per hour, which is already close to the top speed of our fastest interplanetary probes and roughly 50 times faster than a commercial jet, you're still looking at a travel time of around 80,000 years. That is 8 times longer than the entire span of recorded human history. Every city you know, every empire, every technology, all of that fits into a slice of time much shorter than one Proxima B trip at that speed. People sometimes shrug and say, well, we'll just go faster. Okay, so let's look at what faster means in concepts that are actually being discussed. Breakthrough Starshot, for example, is a serious proposal to send gram-scale probes to Proxima Centauri using powerful ground-based lasers pushing ultralight sails. The goal is about 0.2 times the speed of light, 20% of light speed. At that velocity, you can cross 4.24 light years in roughly 20 years. That's impressive, but notice 2 things. First, those are microprobes with masses measured in grams. No life support, no people, no thick radiation shielding, no spare parts, no habitats. Second, even then, you're throwing them across interstellar space with no way to slow down at the other end unless you add even more complexity. Now, scale that up in your head. To move an actual colony, you're not talking about grams, you're talking about megatons. You need kilometers of habitat volume, air, water, food, engines, shielding, structural mass, plus whatever you bring to build shelters on Proxima B itself. There is no drive system you can build with near-term physics that will push that kind of mass to 20% of light speed. Chemical rockets are nowhere close. Nuclear thermal rockets are better, but still far too weak for relativistic speeds. Even advanced concepts like nuclear fusion rockets or antimatter drives are, at best, speculative and still face the problem of building, fueling and safely operating them with civilization-scale resources. So in reality, if you imagine sending actual humans plus all their gear with tech that feels even remotely plausible this century, your velocities are tiny compared to light speed. Maybe a few hundred kilometers per second in aggressive nuclear concepts, maybe a bit more, but still orders of magnitude below 0.2 C. That pushes trip times back into thousands to tens of thousands of years. You're in generation ship territory, hundreds of generations living and dying in a metal tube before anyone even sees Proxima B with their own eyes. And all of this is before you add the extra mass needed to protect those people from cosmic rays and, later, from Proxima's own radiation environment when they arrive. So where does that leave you, if you somehow decide to push ahead anyway? You build a ship, you send it, after many centuries or millennia it arrives, and you start carving out underground bunkers on a high-radiation, atmosphere-stressed, tidally locked world. Now, ask yourself a simple logistics question. What happens when something critical fails? On Earth and in near-Earth space, if a base runs into trouble, you can send help. You can launch resupply missions in days or months. You can move people, fuel, food and hardware around the planet in hours. Earth acts as a giant safety net for your mistakes. On Proxima B, there is no safety net. If you settle there, resupply from Earth is effectively impossible on any timescale that matters to the people living there. If they run out of food, if a key life support system fails, if their radiation shielding is damaged, no one is showing up in 5 years, let alone 5 days, to bail them out. Any cargo mission sent after the initial colonization would arrive long after the original settlers, and probably long after their children and grandchildren, unless you're operating on civilization-level planning times of tens of thousands of years. Practically speaking, once you go, you're on your own. That means every part of your infrastructure has to work almost perfectly in one of the harshest habitable environments we know about. Your farms, whether underground hydroponics or shielded surface greenhouses, have to produce enough food with no large-scale backup. Your atmosphere management systems have to keep the air inside your habitat stable, while the real atmosphere outside is being stripped and chemically altered. Your radiation shielding has to be thick enough and maintained enough to handle a constant storm of flares and particles. Your power systems have to survive geomagnetic equivalents far worse than our worst solar storms. There is no patching problems by buying time from Earth. If something breaks in a way you didn't plan for, people die. Humans, as a species, do not have a good track record of building perfect zero-failure systems. Everything we make fails eventually. Our planes crash sometimes, our power grids go down, our spacecraft malfunction. On Earth, we live with that because we have backups and workarounds. If one city fails, others keep going. If one harvest is bad, another region can help. Earth is our failure cushion. Proxima B offers none of that. You're stacking extreme environment on top of extreme distance, with no margin for error. This is why the "can humans live there" question is much bigger than could a human survive a minute on the surface in a suit. When you ask, can humans live on Proxima B, you are really asking 3 things at once. First, is it physically survivable at all? Can a human body inside a habitat stay alive there with known physics? Second, is it sustainable? Can you maintain that survival for many generations with local resources and realistic maintenance? Third, is it worth it? Does this environment justify the risk and cost compared to places much closer to home? On the first point, physical survivability, the answer is technically yes. With enough shielding, engineering and luck, you could keep small numbers of humans alive there. On the second point, sustainability, the answer gets shaky because now you're fighting radiation, atmosphere loss, climate instability, and lack of backup for centuries and millennia. On the third point, is it worth it? The answer for any civilization remotely like ours is no. Not when you have easier options like building space habitats in your own solar system, or trying to terraform Mars, or constructing O'Neill cylinders with carefully controlled environments at convenient distances. At best, Proxima B is a future scientific outpost target, the kind of place ultra-advanced civilizations might send probes and maybe small crews to study, the same way we station scientists in Antarctica, or run deep sea labs. It is not a natural next home for unmodified humans. Even a civilization far beyond ours, with fusion drives and radiation-hardened megastructures, might look at Proxima B and still decide it is cheaper and safer to build rotating habitats in deep space near our own star. And that brings you to the final step in this whole argument. If Proxima B, the closest so-called Earth-like planet, fails so many tests once you run the real numbers, what does that do to the whole idea of habitable zones and Earth 2.0 hype? It forces you to admit that being in the right place around the right kind of star is only one green light out of many, and Proxima B is a clear example of how getting just that one thing right does not make a world a true home. So after everything you've heard about Proxima B being brutal for humans, there's a different question that's just as important. Could something else live there? Something that isn't like you at all? Many of the climate and escape models agree on one thing. A lot of likely Proxima B states are terrible at the surface, but that doesn't mean the entire planet is dead. If you stop insisting on blue skies and beaches, and you allow life that never sees the sky, the requirements relax fast. Think underground first. Radiation, flares and space weather are surface problems. Go a few meters down into rock or ice, and the particle flux drops sharply. Go tens or hundreds of meters down, and constant radiation from flares becomes almost irrelevant. A thin or even missing atmosphere matters much less if your ecosystem is sealed inside rock pores or under an ice cap. Geothermal heat from the interior can keep pockets of liquid water stable even when the surface is well below freezing. You can imagine subsurface aquifers, brine-filled fractures, or full-on buried oceans under kilometers of ice. We already think moons like Europa and Enceladus do exactly this around Jupiter and Saturn. On Proxima B, models show that if you have a couple of kilometers of ice and a reasonable internal heat flow, you can maintain a liquid layer at the base of that ice for billions of years. In that zone, chemistry doesn't care that the star above is flaring like crazy. Temperature stays stable, radiation is shielded, and chemistry can run. For microbes, that's enough, so from an astrobiology standpoint, Proxima B could be interesting even if the surface is a nightmare. Subsurface oceans, salty brines, hydrothermal systems along deep fractures, these are all potential habitats. They don't need blue sky, they don't need mild UV, they just need liquid water, energy sources, and time. Proxima's absurdly long stellar lifetime means time is not the limiting factor down there. What about photosynthesis, though? Could anything actually use Proxima Centauri's light the way plants use the sun's? Some research is already asking that. M-dwarfs like Proxima are cooler. They emit more light in red and infrared, less invisible and ultraviolet compared with the sun. That doesn't kill photosynthesis by default. It just shifts the game. There are still photons, just at different wavelengths. Pigments tuned to red and near-infrared light could, in principle, drive oxygen-producing photosynthesis under a red dwarf. And then there are the flares. They are bad for you, but for hypothetical life, they might be an opportunity. Flares dump bursts of higher energy light into the system, including UV. A biosphere around Proxima Centauri could adapt to that pattern. Organisms could live underwater, where water filters the harshest UV, but still lets useful light in. They could evolve pigments that protect against radiation but still harvest energy. They might switch between active and dormant states depending on flare cycles, going quiet during the worst events and ramping up when the radiation drops. From a pure science angle, that's fascinating. You get to ask questions like, what does chlorophyll look like on a red dwarf world? Do you get black plants that absorb everything? Or red-shifted pigments tuned to the star's spectrum? How do protective pigments and photosynthetic pigments co-evolve? Could organisms use flare spikes as timed energy bursts? These are the kinds of problems that make exoplanet biologists excited, because they push life into regimes we've never seen but that physics doesn't forbid. But now bring humans back into that picture and look at the mismatch. Technologically, we can live in submarines. We can live in underground bunkers. We can seal ourselves into habitats where we control the atmosphere, temperature, and light completely. We already do small versions of that on Earth in research stations and submarines. So you might think, fine, if Proxima B has a subsurface ocean or niche habitats, we'll just drop in and share the planet. Biologically, though, your default environment is very specific. You're optimized for an Earth-like surface niche, roughly 0 to 3 kilometers above sea level, about 1 bar of pressure, a nitrogen-oxygen atmosphere with around 21% oxygen, temperatures around 20 degrees Celsius, about 68 Fahrenheit, and moderate UV with a stable day-night cycle. Your sleep cycles, your hormonal rhythms, your bones, your lungs, all of that expects the band of conditions. You can handle some variation, high altitude, polar winters, tropical heat, but you are still oscillating around that same central template. Proxima B, in almost all realistic scenarios, does not naturally give you that template anywhere on its surface. You might be able to manufacture it in sealed habitats, but that means forcing humanity into a permanent state of exile from the actual planet. You wouldn't be living on Proxima B in the way humans live on Earth. You'd be living inside metal and rock bubbles, isolated from the external environment, with the outside treated as hostile, permanently. That is a fundamentally different mode of existence from anything in your evolutionary history. And if the planet already has its own biosphere, That complicates things in a different way. If Proxima B hosts microbial life in subsurface oceans, in brines, or in geothermal pockets, that life is probably adapted to conditions you find lethal. High radiation tolerance, low or no sunlight, extreme chemistry, maybe very different pH or salinity levels. For science, discovering such life would be huge. It would show that biology arises more than once in the universe, that Earth is not unique. It would be one of the most important discoveries humanity could ever make. But that discovery does not magically convert the planet into a good home for you. If anything, it makes it more ethically and practically complicated to terraform. Terraforming Proxima B to create an Earth-like atmosphere and surface would mean radically changing or outright destroying any existing alien ecosystems. You'd be talking about wiping out an entire independently evolved biosphere just to make a hard, marginal world slightly less hard for humans. So the most likely story, if Proxima B has life at all, looks like this. Life is microbial, maybe a bit more complex in lucky niches, living underground, under ice, or in specific chemical environments, entirely adapted to the red dwarf spectrum and the planet's extreme conditions. It never sees open blue skies, it never walks on continents, it might never build anything you'd call civilization. From our point of view, it's fragile and strange. From its point of view, we're the ones who don't belong. That kind of life would be priceless to study, but it doesn't change the core verdict about human habitability. A planet can be alive and still be a terrible place for us to live. In fact, the more interesting its native biology is, the less justifiable it becomes to bulldoze it with terraforming schemes just so humans can have another rocky world. And that brings the focus back to the larger lesson Proxima B is already forcing on us. We can't just chase the word habitable and assume it means good for humans. We need a much stricter checklist if we're serious about finding actual second homes, not just alien laboratories. You keep hearing that Proxima B is in the habitable zone. So how can it still be such a bad place for humans? That's the core misunderstanding this planet exposes. By the simplest definition, the habitable zone is just the band around a star where a rocky planet could, in theory, have liquid water on its surface if everything else goes right. Proxima B sits inside that band. The energy it receives, about 65 to 70% of what Earth gets, is in the right range for liquid water on a rock. So yes, by that one metric it qualifies. But step back and look at everything else you now know about this system. The star bombards the planet with extreme X-ray and ultraviolet radiation. The stellar winds are thousands of times stronger than what Earth sees. The planet is probably tidally locked, with one side in eternal day and the other in eternal night. Flares and superflares are routine. All of those factors directly attack the atmosphere and the surface. So Proxima B hits yes on the basic energy requirement, and probably no on almost every other condition that matters for human life. It's the perfect example of why in the habitable zone by itself is not enough and can actually be very misleading if you don't look deeper. So going forward, if you're serious about finding worlds where humans could actually live, you need a tougher checklist. Think of it as needing 4 green lights, not 1. First, yes, you still need the right stellar flux, the right amount of energy. Too little and everything freezes, too much and you risk runaway greenhouse states. Second, you need a host star with moderate activity, not a star that spends billions of years in a hyperactive state throwing out constant X-rays, UV and particle storms. Third, you need a planet that can hold a thick atmosphere for billions of years, not just a few million, under that star's behaviour. Fourth, you need a magnetosphere and space weather environment that don't constantly shred that atmosphere or slam the surface with radiation. Proxima B clearly passes the first one. It gets the right order of magnitude of energy. The rest are questionable or outright bad. The star is very active. Long-term models show atmosphere loss can be huge. Magnetohydrodynamic simulations say the stellar wind crushes the magnetosphere close to the atmosphere. Space weather is extreme, so when someone calls Proxima B potentially habitable, they're usually talking about that first box only. the simple energy argument. From a human point of view, that's not enough. You care about whether air, water and climate survive for billions of years, not just whether the star is bright enough and not too bright. This has a direct implication for where you should actually focus if you're hunting for Earth 2.0 in the human sense. Red dwarfs like Proxima are great for telescope surveys, because their planets are easier to detect, and transits block a bigger fraction of the star's light. But their environments are harsh. If you want genuinely human-friendly targets, Sun-like G-stars and slightly smaller K-dwarfs are much better bets. They are less flare-happy than M-dwarfs, their habitable zones sit farther out, and the stellar wind and radiation environment at those distances are usually calmer. Around a G or K star, you're more likely to find planets where the habitable zone is wider. The star's early active phase is shorter or less intense, and the planet can keep an atmosphere for billions of years without being stripped. That doesn't guarantee an Earth twin, but it moves you closer to the conditions you know work. Proxima B, sitting right next door at 4.24 light-years, makes this contrast painfully clear. The nearest habitable zone planet is not automatically the nearest human habitable planet. The closest truly human-suitable world might be tens or hundreds of light-years away, around a quieter star, and you may not have found it yet. This is the shattering realization Proxima B forces on you. At first, the story sounded simple and hopeful. Earth, mass, planet in the habitable zone in the nearest star system. That combination triggered a lot of people to jump straight to future home, but when you actually break it down, the data say something very different. They say, this planet is an extraordinary scientific target. It might have exotic climates, strange chemistry, maybe even life in extreme niches. It is a fantastic laboratory for testing your theories of atmosphere loss, red dwarf space weather, and climate under tidal locking. At the same time, by every realistic metric that matters to unmodified humans, it is a terrible place to live. The star is too active, the radiation is too high, the atmosphere, if it still exists, is too fragile or too altered. The climate, in the best cases, is too constrained and sensitive. The surface is too exposed. Calling it another Earth hides all of that behind one nice-sounding label. As a spacefaring species, you don't get to ignore those details. Proxima B is essentially telling you to grow up. You can't treat catchy headlines, Earth-like planet next door, as colonization plans. You have to deal with the actual physics, the real radiation numbers, the real climate behavior, the real atmosphere loss timescales. You have to accept that a world can look promising at first glance and still be fundamentally wrong for you. And that brings you to the final step in this whole argument. If Proxima B is not your future home, then what is it to you, really? A warning label? A test case? A dead end? Or is it something more useful and more honest? A nearby laboratory that shows you exactly what can go wrong when you chase Earth-like planets without asking the harder questions first? So when you strip away the hype and just line up the hard numbers, what does Proxima B actually give you? It sits very close to the right size, with a mass and radius in the Earth-like range. That means surface gravity probably between about 0.9 and 1.4 g, something your bones and muscles can handle. It orbits in the classical habitable zone by simple energy rules, getting about 65 to 70% of the sunlight equivalent that Earth gets. On a quick chart, those two facts look amazing nearby, Earth-sized in the habitable zone. That's the part everyone repeats. But sitting underneath those nice numbers are the ones that kill the dream. Long-term modelling says Proxima B is hit with roughly 10 to 60 times Earth's X-ray and extreme UV radiation. Its stellar wind environment is not a little stronger than ours. It's more than 2,000 times Earth's solar wind pressure in many simulations. It likely spins in a tidally locked or near-locked state, one face in constant day, one in constant night, under a flare star that throws major outbursts on the timescales of hours. Put that together, an atmospheric escape is not a small correction, it's a main feature. Radiation damage is not an edge case, it's the baseline. Climate fragility is not an exotic scenario, It's what you expect as soon as you run the models. From those ingredients alone, you don't have a stable, forgiving Earth cousin. You have a world that has spent billions of years being eroded, heated, and stressed in ways Earth never had to deal with. If Proxima B still has an atmosphere, that atmosphere has survived a constant attempt to strip it away. If it still has surface or near-surface water, that water has done so under huge XUV doses and strong winds. You're not asking maybe there are a few issues, you're asking, is there anything left that looks like the environment humans actually need? So what does it really mean to say humans can live there in a serious, non-clickbait way? It does not just mean a human in a high-tech suit could stand there for 10 minutes and not die. It means you can support generations of people with reasonable effort. For that, you want at least 3 big things. First, a thick, stable atmosphere that can stick around for billions of years, not just a few million. Second, surface radiation levels low enough that people can live and work outside with modest protection, not meters of rock above their heads. Third, wide regions of land and water with moderate climates, enough area for agriculture, cities, industry and redundancy if one region fails. Proxima B in almost every realistic scenario that comes out of current models misses those targets. The atmosphere either gets heavily eroded, or it shifts into a state that is chemically and thermally hostile to you, like a cold, dense, oxygen-heavy mix you can't breathe. The radiation environment is so intense that even with some atmosphere left, you are pushed into underground or heavily shielded living as the default. The climate, even in the optimistic eyeball ocean cases, gives you a limited dayside patch of liquid water, surrounded by deep cold and permanent night over most of the rest of the planet. Yes, you can imagine a far future civilization building bases there. They could bury habitats under many meters of regolith, build thick domes, run fusion, or advance reactors for power, and engineer everything to tolerate flares and storms. You could run it like an off-world Antarctica, with a small rotating crew and extreme safety procedures. But there's a big gap between we can force a small number of people to survive there with industrial-level support, and this is the next Earth. Proxima B never crosses that gap. You cannot honestly sell it as a place where large populations of unmodified humans can live in a way that feels even remotely natural. That is why the most honest way to think about Proxima B is not future colony sabor, but nearby experiment. It is not your next address. It is your nearest exoplanet laboratory. It is the place where your telescopes and later your probes will stress test everything you think you know about red dwarfs and their planets. You use it to study how atmospheres live or die when a planet is parked this close to a small active star. You use it to see how often any water survives, whether as oceans, ice, or hidden subsurface layers. You use it to check if life can adapt to violent space weather, and if so, where it hides and what it looks like. Proxima B is also where you learn how dangerous your own language can be. The word habitable sounds friendly, but here it mostly means gets the right amount of starlight if all the hard problems magically solve themselves. This planet forces you to confront the gap between habitable zone on a diagram and actually works for humans on the ground. It shows you how easily Earth mass plus habitable zone plus nearby can turn into a trap if you ignore radiation, winds, tidal locking, and long-term stability. In that sense, Proxima B is the planetary version of a crash test dummy. You don't buy a car and immediately drive it into a wall. You test other cars, you push them to failure, you see how and where they break, and then you design something safer. Proxima B lets you crash test your assumptions about red dwarf planets at close range. You get to watch what the extreme space weather does to a supposedly habitable world right on your galactic doorstep, with future instruments that can measure its atmosphere, its chemistry, maybe even its surface conditions, and all of that has one clear payoff. When, centuries from now, your telescopes or your probes finally pick out a different world, maybe around a quiet K-type star, with gentle space weather, a broad habitable zone, a stable oxygen-nitrogen atmosphere, and a climate that looks robust over billions of years, you will recognize it. You will know that that planet checks more than just the right flux box. It will check the stellar activity box, the atmosphere retention box, the space weather box, the climate stability box. When that happens, you will understand that this quieter, farther world is a real candidate for where humans might truly belong beyond Earth. And you will also understand that Proxima B, despite being closer, was never that world. It was the warning sign you needed, the nearby case that forced you to raise your standards and stop confusing possible liquid water somewhere with a world where people can actually live. This video is for educational or entertainment purposes only, and information provided in the video may be incorrect. Like the video and subscribe to the channel for more such amazing videos.